Heat versus temperature, a cosmic misunderstanding. Space is often perceived as a cold and unforgiving environment. This perception stems from a misunderstanding of the difference between heat and temperature. Heat is the total energy possessed by the molecules within an object or system. Temperature measures the average kinetic energy of those molecules, essentially how fast they are moving. Imagine a pot of boiling water. The water molecules are moving rapidly, resulting in a high temperature. However, if you were to dip your finger into the pot, the amount of heat transferred to your finger would depend on how long it was submerged. In the vast expanse of space, the situation is reversed. The sun emits an immense amount of heat, traveling through space as radiation. However, space itself is a near-perfect vacuum, meaning there are very few molecules to absorb this heat. Consequently, while the sun's radiation carries a tremendous amount of heat, the temperature of space remains extremely low. The vacuum of space, a poor conductor of heat. Heat can travel in three ways: conduction, convection, and radiation. Conduction is the transfer of heat through direct contact, like touching a hot stove. Convection is the transfer of heat through the movement of fluids, like hot air in an oven. Radiation is the transfer of heat through electromagnetic waves, which can travel through the vacuum of space. The vacuum of space is an efficient insulator because it lacks the necessary medium for conduction or convection. This leaves radiation as the primary means of heat transfer in space. Imagine standing around a bonfire on a cold night. You feel the heat primarily through radiation. Similarly, objects in space closer to the sun receive more intense radiation and therefore have higher temperatures. This is why astronauts wear specialized suits with thermal control systems to regulate their body temperature in space. Earth's atmosphere, our planetary blanket. Earth's atmosphere plays a crucial role in regulating our planet's temperature. The atmosphere is a mixture of gases, primarily nitrogen and oxygen, that surrounds the Earth. These gases absorb and scatter incoming solar radiation, preventing all of it from reaching the Earth's surface. The atmosphere acts like a giant blanket, trapping some of the sun's heat and keeping our planet warm enough to support life. This phenomenon, known as the greenhouse effect, is essential for maintaining a habitable temperature range on Earth. The atmosphere also plays a vital role in distributing heat around the globe. Warm air from the tropics rises and flows towards the poles, while cooler air from the poles sinks and flows towards the equator. Furthermore, the Earth's atmosphere protects us from harmful radiation from the sun. The ozone layer absorbs most of the sun's ultraviolet radiation, which can cause skin cancer and other health problems. The sun's energy, a matter of perspective. From Earth, the sun appears as a bright yellow disk in the sky, providing warmth and light. However, the sun's energy is not evenly distributed throughout space. The intensity of solar radiation decreases with distance from the sun, following the inverse square law. This means that an object twice as far from the sun will receive only 1/4 of the solar radiation. Imagine a flashlight beam. Close to the flashlight, the beam is intense and concentrated. However, as you move the flashlight farther away, the beam spreads out and becomes dimmer. The same principle applies to the sun's energy in space. Internal heat generated by radioactive decay within a planet or moon can also contribute to its overall temperature. Additionally, the albedo, or reflectivity, of a celestial body's surface can affect how much solar radiation is absorbed or reflected. Space exploration presents unique challenges due to the extreme temperatures found beyond Earth's atmosphere. Designing spacecraft and equipment capable of withstanding both the intense heat of direct sunlight and the frigid cold of deep space requires innovative engineering. Spacecraft often utilize specialized insulation materials and thermal control systems to regulate their internal temperatures. One example is multi-layer insulation, MLI, which consists of multiple layers of thin reflective material separated by a vacuum. MLI is highly effective at preventing heat transfer through conduction and convection. Heat pipes are another technology used in spacecraft thermal control systems. These sealed pipes contain a working fluid that evaporates at a heat source and condenses at a cooler location, transferring heat efficiently. future missions to the outer solar system will need advanced thermal control systems to keep spacecraft and instruments operational. The development of new materials capable of withstanding extreme temperatures will be essential for enabling human exploration of Mars and beyond. Despite these challenges, space exploration offers immense potential for scientific discovery and technological advancement. The concept of a lunar elevator, a transportation system connecting Earth to the Moon, has captivated the imaginations of scientists and science fiction enthusiasts alike. While still theoretical, the lunar elevator represents a potential game-changer for space exploration. The basic principle involves a tether anchored to the lunar surface and extending beyond the L1 Lagrange point. A counterweight at the tether's far end would maintain tension, while climbers would ascend and descend the tether. The construction of a lunar elevator presents numerous engineering challenges, including the development of materials strong enough to withstand the immense tensile forces. Carbon nanotubes have emerged as a potential candidate for the tether material. Despite the technical hurdles, the potential benefits of a lunar elevator are vast, enabling the establishment of a permanent lunar base and facilitating resource extraction. As we continue to push the boundaries of space exploration, the development of advanced propulsion systems will be crucial for enabling human missions to Mars and beyond. Traditional chemical rockets are limited by their fuel efficiency and the vast distances involved in interplanetary travel. Scientists and engineers are exploring alternative propulsion technologies. One promising avenue is nuclear fusion propulsion, which harnesses the energy released when atomic nuclei combine to produce thrust. Fusion reactions release far greater energy than chemical reactions, potentially enabling much faster travel times. Another concept is antimatter propulsion, which exploits the extraordinary energy released when matter and antimatter annihilate each other. Producing and storing significant quantities of antimatter remains a major obstacle. Other innovative ideas include solar sails, which harness the momentum of photons from the sun to generate thrust, and beamed energy propulsion, using lasers or microwaves to propel spacecraft remotely. Continued research and development in space exploration are essential for expanding our understanding of the universe and addressing challenges on Earth. Space exploration drives technological innovation, leading to breakthroughs in fields such as communications, medicine, material science, and energy. Satellite technology has revolutionized communication and navigation, enabling global connectivity and disaster relief efforts. Medical advancements like MRI and CAT scans have roots in space exploration technologies. The search for life beyond Earth has spurred advancements in astrobiology and the study of extremophiles. Understanding how life can exist in harsh conditions could provide valuable insights into the origins of life on Earth. By investing in space exploration, we invest in our future, fostering innovation and expanding the frontiers of human understanding. Space exploration has a unique ability to inspire and engage people of all ages, igniting a sense of wonder and curiosity about the universe. Iconic images of the Earth rising over the lunar horizon and views of distant galaxies have captivated generations, educating and inspiring the next generation of scientists, engineers, and explorers is crucial for the progress of space exploration. Programs that promote STEM education play a vital role in nurturing curiosity and fostering a love of learning. Encouraging diverse perspectives in STEM fields is essential for driving innovation and tackling the complex challenges of space exploration. By investing in STEM education and outreach, we can empower future generations to reach for the stars. The vast expanse of space, with its extreme temperatures, may seem cold and unforgiving. However, it is also a realm of endless wonder, filled with mysteries waiting to be unraveled. Understanding the physics of heat transfer in space is crucial for comprehending the dynamics of the cosmos. The pursuit of space exploration is about expanding the frontiers of human knowledge and unlocking the secrets of the cosmos. The universe awaits, and it is up to us to embrace the boundless opportunities that lie ahead.